Okay, again, this is Nick from the core team.
Hi, thank you. So I'm going to make my excuses before I even start. Is using this other computer, I don't have my notes. So if I miss and forget and stumble, you have to forgive me. People choose Rust for lots of different reasons. It's memory safe, it's fast, there are no GC pauses, and so on and so forth. But you wouldn't use it if it were painful to use. I look forward to programming in Rust. I get up in the morning and I go to work and I think, yeah, I get to use Rust today. It's a good day. And I don't think like that about every programming language. And apparently I'm not the only one, because for the 4th year in a row, the Stack Overflow Developer Survey has picked Rust as the most loved language. So in the talk today, I want to try and say how we got to this point.
Can you say that to this so that our translator can hear you?
Sure. I have to stand closer to the mic. Okay. So, I think one of the main reasons that Rust is a delightful language to use is because the Rust community has always tried to make it a delightful language to use. And this sounds kind of obvious, but it's very easy to get caught up in what's the most elegant solution or what's the most technically pleasing solution to a problem, and not what will make it the user the happiest. Ever since kind of the very first days of Rust, there's been this emphasis on making it a practical language. It was never set out to be kind of like primarily like an academic thing or something. In the run-up to the 1.0 release, this is why I need the notes. Sorry. So in the run-up to the 1.0 release, there was like a huge effort to actually get something released. There was like we needed to kind of like get all these kind of moving parts in the language and the libraries all working together. But there was also this sense that like once you have the 1.0 release, you can't go back. We've got this backwards compatibility guarantee, and it's not good enough to make just a language which exists. It has to be kind of pleasant to use it. And then after the 1.0 release, there was a period where we were kind of like landing some more big changes. And in, I think, 2017, we announced the ergonomics initiative, which was to refocus on usability and the ergonomics of the language. And it was kind of between kind of like the 1.0 release and the ergonomics initiative that this idea of programming language ergonomics really became kind of a fundamental goal for the language. And now we had the 2018 edition release, and we're kind of in another phase where I think we want to kind of like look away from the big things and look at making the usability of the language much better again. Okay, so for the rest of the talk, I'm going to start by going over some general issues around ergonomics, and then in turn I'm going to look at the tools, libraries, and the language itself, and how we think about ergonomics within each of these domains. Okay, so ergonomics is usually something you think about with hardware. You'd say, like, this is an ergonomic chair or an ergonomic keyboard. What does ergonomics mean for a programming language? And primarily, it's the language helps you to be efficient. There's an absence of friction, and we prevent you getting injured in some way, whatever that means for a programming language. A little bit more concretely, we think that the language is an ergonomic one when the code you write closely matches the mental model of the program that you have in your head. An example of this is if you want to have data that can represent multiple variants, then you can write this using kind of classes and inheritance, and it works. But in Rust, we give you enums, and enums and variants much more closely match that mental model. And so this is reducing friction and making your program easier to reason about. But I said at the beginning that one of the reasons we've ended up with a language which is, I think, quite pleasant to use is because we've focused on that. So why doesn't everybody focus on it? Well, I think one reason is it's really difficult. Ergonomics is all about people. It's about your users. And anything to do with people is always difficult because people are complicated and all people are different in some way. And it's especially for people with a very technical mindset often, it's difficult to think about these issues. It's full of gray areas and fuzzy questions, and there's no like hard answers. It's just all kind of trade-offs. And there's a lot of context. What works well for one library might not work in another library. What works for one programming language might not work in another one. So just because something's ergonomic in, say, Python, doesn't mean that it's ergonomic in Rust. And there's all sorts of cross-cutting concerns and intersections. For example, if your user is using an IDE, as opposed to, say, Vim, then you're going to have a very different experience of what's ergonomic in the language and what's not. So if it's so difficult, how do we actually make decisions about this? In an ideal world, we'd be very scientific. We'd conduct user studies. We would come up with, evidence and data and so forth. But this is actually really difficult. It's a set of skills that have not really existed in the Rust community, and more importantly, we just don't have the resources to do this kind of work. And even if we did, even if you have some nice, crisp scientific answers, well, you still have, which users do you study? Which questions do you ask? And so forth. Thinking about use cases can help. But there is a risk there that you over-specialize, that language design by kind of addressing use cases generally doesn't work out so well. But we can also explicitly ask users, and even when we don't ask, we get plenty of feedback through the RFC process and other channels. And there's a lot of Rust code that already exists. We can look at how people use Rust today or have used Rust in the past. And with tools like Crater, we can actually look at almost the entire ecosystem of Rust code. But the really most important tool, I think, is empathy. And this is, for any of the Rust design teams, being able to kind of use empathy is a really important skill. And it's about being able to imagine who your users are, what their environment is, what their background is, and what problems are they trying to solve. And then put yourself in those users' positions and use that to kind of drive your decision-making. Having said that, there are some kind of principles and heuristics that I and I think others in the Rust leadership teams kind of stand by, and throughout the talk I'm going to try and highlight some of these. The first one is that doing the right thing ought to be the easiest thing to do. The complication, of course, is what is the right thing. Often it's the most performant thing or the safest thing. Important things should be explicit. And there's a corollary to that, which is that things that are not important should be implicit. You shouldn't have to write lots of boilerplate or go through lots of ceremony to get your work done. Again, this begs the question, what's important? And this is a really hard question because it gets back to every user being different. What's important for one user might not be important for another. And, well, so one thing that, just to pick kind of something concrete that is often important in Rust, ownership, borrowing. These are really important concepts in Rust and are often things that we want to make explicit. Okay, so I'm going to start by talking about tools. One of the core principles in developing the Rust tool ecosystem has been to put the user first. And again, this sounds a really obvious thing, but there are lots of other kind of design constraints. Do you want to make your tool fast? Do you want to make your tool scriptable? Should the output be machine readable? These are all important goals, but I believe they should be secondary. What's really important is the user interacting with the tool should have a good experience. A principle that we come back to again and again is consistency. For tools, that means if a tool can do multiple different things, then it should do them in a similar way. And between tools, we should try and stick to the same kind of user experience. And this makes the tools ergonomic because you spend less time looking up how a tool works, and you can apply the usage patterns you've got from using other tools. So when you come to a new tool, it should just work. It should be intuitive to you. Another principle that we usually stick to is convention over configuration. We're not extreme about this. We like to offer you ways to configure your tools because that's important. Every user is different. Every user is trying to do different things. But the idea is that if you're doing something common, then the tool should just work. You should not have to create a configuration file if you're using a tool in the normal kind of way. So I want to go through an example to show how these principles apply in practice. Let's say you want to format some code. Well, you can use the Rust format tool to do this. And in order to make it, you have to install this tool on your computer. And in order to make this whole flow as easy as possible, we provide a tool for installing these tools. Okay, so you run Rust up. And this is the same thing you would run Rust up to install other tools and to install things like source code. Once it's installed, and hopefully that was easy to install it, running Rust format is consistent with other cargo commands. You run it just like you would run cargo build. You run cargo format. And sticking to the convention over configuration principle, when you do this, it should do the right thing. If you have a regular cargo project, it will reformat the whole project and nothing more. And the formatting we use is hopefully something that you will approve of. It's a sensible formatting, which you can configure if you really want to. And if you do have to do something unusual, if you do need to pass some arguments to Rust format, then you can do that using the same arguments that you would pass to cargo build. So there's consistency between these different tools. A last principle I want to mention about tools is that tools are not just kind of like a robot or a hammer or something. It's the tools can teach the user. And the best example of that is Rust error messages. So we can see this is the Rust error message from a few years back, and this is how it looks today. A lot of people have put a lot of effort into making our error messages great. And The best example is probably borrow checking. Borrow checking is something a lot of people struggle with in Rust, especially as they're learning the language. It's a pretty unique concept. And so we put a lot of effort into the error messages, not only to clearly explain the error, but to help you learn from your mistake, to not make that mistake again, to better understand what's going on inside the compiler. And it's been a lot of work to do that. It's not just about writing a nice message. There's fundamental work in the compiler that make the compiler more complex in order to give you better error messages when you get a borrow check error. And that's a great example of the ergonomics being a priority when we're doing kind of design work in the same way that performance is. Next up, I want to talk about the libraries. Again, consistency is a really important principle here. And for libraries, this means consistency of naming. It means consistency of usage patterns. So if you're used to using a vec, then when you start using a hash map, it'll be a similar experience. And it means consistency in the declaration patterns as well. So when you're reading the documentation or the source code, you don't have too much friction between different data types or different functionality. Another principle is to minimize duplication. A good example of this is prior to 1.0, there were 7 different find methods on HashMap. 7. And they were all doing essentially the same thing. They were just doing a find, but with slightly different semantics around referencing or ownership or something. And that's very unergonomic because there's friction there. You have to work out which one you're going to use. You have to stop and think, do I use this find or this find? Well, all you want to do is find a value. That's unnecessary ceremony because you're focusing on what's not important. Okay, what's important is finding a value, and what's not important in this case is the state of the key. I want to kind of dig into this with an example. So here we've got a hash map. It's a mapping from strings to integers. Perhaps we're counting the words in a document or something. And looking at the signature of hashmap here, you would expect to take a string. And indeed, if you can call get like this, where we take a reference to a string. But it's actually much more common to use this type, right? Which is a reference to a stir. So how do we handle this? Note that this is not just a type and a reference to a type. These are 2 distinct types that are related in some way. And just to make it more complicated, when you insert something into the hash map, you don't want to allow a reference. You want to only have the owned type. And here, the ownership is important. And so you do have to think about it, because if we let you pass references, then the hash map would have to clone that reference, and that can be a really expensive operation. So that's something that is possibly important for users to know about, and so we make our users be explicit. So how do we kind of make all this work? Well, so let's have a look at the signature for hash map. This is kind of a slightly simplified version of the real hash map, by the way. So this is just a hash map from keys with type K to values with type V. And this is what the get method looks like. And what's interesting here is you might expect get to take a reference to K, but it doesn't. We have this new type, Q, and we take a reference to Q, and we use the trait called borrow to relate the types K and Q. We say that K can be borrowed as Q. And there are implementations for stuff like string and stir to make this connection. And that's kind of complicated. I'll just go back a second. This is kind of complicated. You may well say, well, this is not very ergonomic, and you'd be right. But it does let this example work, and I think that this usage is very ergonomic. And furthermore, not only does it work with strings, but it works with vecs and slices, and it works with all your other reference types as well. So there's consistency here, as well as eliminating duplication. And this is, leads to another heuristic, which is that if you have to trade off complexity in a library versus complexity in a client, put the complexity in the library. Because hopefully many more people will use your library than write your library, right? And usually, library authors are much more experienced developers and can better handle that complexity. All right, let's talk about language. Language is really about trade-offs. A kind of really classic kind of trade-off I'll start with is kind of, do you want to make a general solution or a very specific solution? General might give you kind of less duplication, but specific might be easier to understand. So error handling is an example of this. In Haskell, you have do notation, which handles any monadic type. This is extremely general. In Java and JavaScript, you have syntax like throw, which is extremely specific to exception types. In Rust, we've picked the question mark operator, which is somewhere in between. You can supply your own generic error types. You're not trapped into the Rust ones, but and it works with option, for example, but you don't have the full generality of do notation. Another trade-off is, do you want a simple analysis? So the compiler is doing an analysis that the programmer can actually understand, or do you want something to be easy to use? An example of this is the borrow checker. Prior to the 2018 edition, we had lexical lifetimes, which as a concept are pretty easy to explain. It's not an easy concept to explain, sorry. It's relatively easy. Since the 2018 edition, we have non-lexical lifetimes, NLL, which is much harder to explain. I could not sit down and explain it to you. But it does make your programs easier to use. It's often more ergonomic to use NLL because you have to worry less about some borrowing errors. And then the biggest trade-off of all is between explicit and implicit. An example of this in Rust is you usually don't need to annotate when you move a value. So the difference between move and copy is implicit. But you do have to annotate when you borrow a value. And so the difference between a borrowed reference and an owned reference is explicit. And getting back to what's important, it's the ownership that's important in Rust. And so that's why you have to make explicit whether something is owned or borrowed, but whether it's moved or copied, we think is not as important. So that is left implicit. I'm going to try and put all this together with another example. This is a common way to match an expression. This is pre-2018 edition code. And what's really important here? Well, the important thing is that you're matching, you're doing some pattern matching, and you've got the two variants, sum and none. And in the sum case, you're binding the variable x. What's not important? Well, exactly, like the fact that x is going to end up borrowed is kind of important, but we know that. What's not important is exactly how that borrowing flows from the outer x variable into the matched variable. Okay, this is just kind of type Tetris. You just have to play until you get it right, usually. And so with the 2018 edition, we've eliminated that. We think it's not important, so you can leave it implicit and concentrate on what's important. And hopefully this is easier to write. You don't need to worry about this stuff. And it's easier to read. There's less distraction. The downside is that the analysis the compiler doing has got more complex. Okay, so what does the future hold? Are we done? I mean, it's apparently a well-loved language already. Well, we're not, obviously. A core principle of Rust is about stability without stagnation. We want to maintain backwards compatibility, but we also want to keep making Rust better. And that's particularly true in the areas of ergonomics. Unfortunately, this gets more difficult as you get more and more users, and those users have relatively more and more experience. There's a lot of kind of pushback, stop energy on what you can do because people know how to do stuff. They've got used to it. What might be a total showstopper for a new Rust user is just a paper cut for an experienced Rust user. And if it's not a problem for them, they don't want change for the sake of change because change is painful. But we want to continue making positive change. We want to continue making Rust better. So a few things that we might do, not saying that we will. I talked a little bit about error handling earlier. Well, I still think that it's not perfect. To me, if I've got a function that looks like this, there's a lot of boilerplate there. Why do I have this OK and all these parentheses at the bottom? Like if I'm not doing the error handling, I don't need to put the parentheses there. And why do I need to declare a result? It's like if we're thinking about convention over configuration, 99% of the time you are using result. Why do I have to write that out? So maybe we can do something about that. Here's another case. Why I said earlier that it's often important that you know whether something is borrowed or owned, but if it's a copy type, it doesn't really matter. So why, when I expect a reference, do I have to explicitly borrow a copy type when it makes no difference to the caller? This is another kind of useless ceremony. So maybe we can do something there. And async await is probably the most exciting thing to happen to Rust since the 1.0 release. And this is all about ergonomics. You can write using futures today, and it works. It's fine. It's very fast. It's very safe. But it's not very ergonomic. It's a pain to write all your futures code. With async await, we make things much more pleasant. On the tool side, our errors are still not perfect. I would not think this is a useful error. We can do better. Okay, that's the whole talk. Just to summarize, well, there's no easy answer. There's no easy takeaway here. Working with users, making things usable is hard work. You need intention. You have to want to do it. You need to keep putting the effort in to make things better. And the key tool you have to make things better is empathy. And you need to relentlessly focus on what is important. And what is important for your users, not what is important for you, or you and your friends, or you and your colleagues, or something. Okay, that's everything. Quickly, I just want to thank Brian Anderson and Nico Matsakis, who gave some really valuable input to this talk. And I want to thank you all for sitting through it. Thank you.
现在是我们的 Q&A 环节，然后大家有什么问题想要问的，举手。对，我们工作人员会递上麦克风。
Hello, you say that API consistency is very important in library, but some consistency is ensured by the design of the library developer. Now, such as the flat map method on option, on result, on iterator, or other things. Do you think that Rust should import some high-order traits abstractions such as functor, applicative, or monad in Haskell to force the library developer to keep the API consistency explicitly. Yes, this is my
Thanks.
question.
That's an excellent question. Just to repeat for the audience, the gist of the question is, should we be using kind of more sophisticated type system things like higher kinded types or functors and so forth in order to enforce generality across the libraries? And I think this gets back to yet another trade-off, which is, do you want to make your code as reusable as possible, even if that comes at the expense of a more complex type system? Or do you want a really simple type system where you lose some safety or you lose some reusability? And like with a lot of things, Rust is somewhere in the middle. We do have very expressive generics, but we don't have higher kinded types. And at the moment, we think that that is the right place on that spectrum. There are a few things coming up, like generic associated types, which move us a little bit kind of further towards more generality. But in general, I think that things like higher kinded types are not a good fit for Rust. And again, it's getting back to kind of like the beginning of the talk, I said that context was really important. What works really well in Haskell, what is really ergonomic in Haskell is not necessarily really ergonomic in Rust. And I think, yeah, things like explicit monads or higher kinded types are not a good fit for Rust.
Okay, thank you.
好，还有其他小伙伴有问题吗？
Hello, Nick. I enjoyed your talk. Thank you.
Thank you.
So I'm completely new to Rust, but before I did C++ a lot. So if I'm considering switching from Rust to Rust, so what kind of specific advantages I can get by the switching? And maybe probably what kind of disadvantages, what kind of shortage does Rust have currently? So thank you.
Sorry, I just get you to repeat some of the question. Like, what kind of shortage? Like, where are we deficient?
Yeah. Some maybe you want to talk a little bit about the shortage of current Rust. So compared to C++, C++ already have a very good, very mature ecosystem. So is there any shortage between compared with C++?
Yeah, I think there's kind of lots, and I wouldn't even know where to start. I think kind of on the language side, sometimes kind of the generics in C++ can be a bit more expressive than they are in Rust, and hopefully we can address that with better procedural macros and generic associated types. Error handling in C++, although kind of exception, I think most kind of like real users of C++ kind of always turn off don't use exception throwing, but this is sometimes more ergonomic than Rust is. I think obviously kind of like the ecosystem is much more mature. You could in C++ you can find libraries that do everything. There's a lot of gaps in Rust support, but that's getting better like literally every day. And on the tools side, the tools are kind of much more mature and more closely suited to C++. It would be great to have better IDE support or debuggers that better understand Rust natively.
Thank you. I know that it takes some time for Rust to get mature. But what's the big advantages, big gets, if I do the switching from C++ to Rust?
So the big gaps?
I mean advantages. So talk about some advantages of Rust compared to C++.
I'm not sure I understand the question very well. Maybe we can talk afterwards and I can answer you better.
Okay, it's okay, it's okay.
Thanks.
好，那个时间关系，我们最后一个问题，好吧？好，大家对，接下来还可以那个继续跟那个交流。
Now we have library like third and some regular expressions. We use procedural macros. And as far as I know, the community and the core team is developing the constant function. Are we migrating from the procedural macro to constant function to make the more ergonomic the language?
No, there are pretty different use cases between the two. I'm not exactly sure how to. Procedural macros allow you to kind of like process kind of like input at compile time as if you were kind of like changing the language, I guess. And that's kind of very different from what const functions let you do, which is kind of much more limited compile time execution. So yeah, they have quite different scopes.
But in my understanding, the constant function is some kind of the constant reflection. Like, for example, if we have a regular expression input to the constant function, we can output the state machine, constant state machine to handle the strings.
I'm not exactly sure for that particular use case, but in general, what you can do with const functions is very limited. I think this is probably, again, maybe something better to take outside, because it's quite a detailed kind of thing to get into. But at the end, like, I think kind of like the big picture is that procedural macros are much more flexible and are much better suited for kind of processing this kind of input.
Oh, okay, thank you.
Okay, thank you, Nick.